Okay, we stop it here in the last class. So in the free body, what is showing, we need to figure out a formula to find the stress in the spring. So spring it carried load, axial load, either tension or compression. So if you apply tension or compressive load in the spring, and depending on the load, it might be failed immediately or it might be failed after certain time. It depends on load, type of spring, and also a type of material. So how it failed? Normally, the wire used to make the spring that is breakdown. It might be any wire in the peripheral area, the wire might be just break, then become two parts. That means complete failure of the spring. So a parts fail or become two parts, that is subject to shear stress. If shear stress works somewhere, then it becomes two parts. So what we did, we took the helical spring. We are thinking applied load on the helical spring is axial load and compressive load. That is showing the red arrow. And load is passing through the centroid of the helical spring. So if we break down right over here with the red color sign, then we need to figure out that what will be the stress right over in the wire. That we need to figure out. So we cut it right over here. So in the upward, from the upward, a downward compressive load F is working, this one. Then it should, if we cut it over here, then this force has to be balanced upward by F. And F is working parallel to the cross section, this cross section. Now, this two force is offset by some distance because this is working upward through this line. And downward force, this is working along this line. So these two force try to tilt the spring in down clockwise direction in this direction. So solid mechanics or strength of material, we talk about the stability of the static body. So this spring is a static body, and normally you'll never see spring is deflecting in sidewise. Okay. So this clockwise moment will create a torque. For bending moment, it will bend some type of bend. But in spring, that we already discussed earlier, that you never see that a spring wire is bent like that. Okay. Or you might, I can say, no, you'll not never see like that. But you see directly a failure or become two part of the spring wire. Now, this torque F into F is, if you think about this is create bending moment, then it will be F into distance. What is the distance? That means this distance from here to here is mean diameter divided by 2. So M equal to mean diameter divided 2. But as I mentioned before, that in the spring there will be no bending moment, but it will create a torque. So instead of M, I'm saying T equal to F into D divided by 2. And what this torque will work. So you see this torque has to carry out by this wire, and this bending working clockwise like this one working clockwise, so the torsion will work anti-clockwise. So you see force, all the torque and force working in this little section is balancing the force F, this force F, and also balancing this torque. Okay. So if we try to figure out the stress in the wire at that location, then see we have two type of load is working there. Number one, direct shear F, which is working parallel to the cross section. So for direct shear, there will be shear stress F by area of the wire. Other thing, there is a torque working. So due to the torque, we know if there is a circular shaft, torque equal to T into R divided by J. So this shear stress due to the torque and direct shear stress, they work together in this cross section. So total shear will be shear stress F by A plus TR, and this R will be radius of this wire divided by J. Okay. From this fundamental formula, we will derive the trace formula for the spring. So if I share the MathCAD file with you, let's see how we can derive it. Okay. Did you see the MathCAD file?
So
You can see, right? Okay.
yes, sir.
Torsional shear stress in a circular rod will have this formula, where R is the radius of the rod, T is the applied torque, J is the polar moment of inertia, and tau is the shear stress due to the applied torque. So right over here, there is a two force working, direct shear and torque. So tau max, that means what will be the maximum shear stress in that portion? TER divided by J plus direct shear F by A. Now T equal to FD by 2. That we already know. Okay. And figure out the area of the wire. Pi by 4 T square. J equal to pi D4 by 32. And this R over here put D by 2. D is the diameter of the wire used to make the spring. So tau maximum part will be maximum you see at the outer fiber, right over here. Shear stress will be maximum. That means right this location, right? At the center, R is 0, right? At the center, we will have only F by A portion. But in the outer fiber, we have both two. That's why outer fiber will be more critical. If it starts to crack, it starts from outer fiber. Now, all these value, this T value, you put over here. R value D by 2, you put it over here. J value, you put over here. And F is actually F, and A equal to pi by 4 D square. So you substitute all the value, then you just rearrange the equation. If you rearrange the equation, you will have this format. And from here, we try to take common F8FD by DV. Take the common. So we take it the common. Right over here, no big D at the bottom over here, right? So you come D by 2D. So if you multiply, you'll get back to this value. Now, we assume a ratio that mean diameter of the spring divided by the diameter of the wire, that is called spring index, d by d. Obviously, it is greater than 1. Okay. So, right, this will be then 1 by c, right? D by small d by big D, 1 by c. So, 2c 1 by c, then you just simplify, it comes in this format. Now, this value we can designate by a correction factor, okay, Ks. So, tau equal to Ks 8 FD into pi d. So, this is the shear stress formula in a spring. You apply tension load or compressive load, shear stress developed in the spring. So, how you get the Ks? By this one. What is the C? Big D by D. Now, there is a one problem that we apply the formula, torsion formula, TR by J, that we learn in the torsion chapter. It is applicable for a straight bar, but in the spring, we apply that wire that is not actually straight, that is a curve, right? And here there is a anticlockwise torsion. So this formula we are applying in a rod, in a circular cross section, but not a straight body. It actually curve. So we are missing some correction. That means our result will not be appropriate if we use this formula, because this formula derived based on applied torque in a straight circular bar. So experimentally, we figure out a onward correction factor, which is called Kc. Okay, it's saying assume the spring wire is straight. It also subject to torsion and direct shear, but actually spring is curved. Curvature in the spring rod increase the shear stress. So due to the curvature, shear stress will increase than applying this formula. T tau equal to TR by J. So we need to multiply by some constant. So this is accounted by another correction factor, Kc, which is known as curvature correction factor. So this is our formula. We multiply this formula by Kc. So this is the formula for the spring. Correction Ks and Kc can be replaced. These two values can be replaced by a common correction factor that is called Kb. So Kb equal to Ks into Kc equal to 4c plus 2 divided by 4c minus 3. Now you might have questioned how we got this value. This is found by experimentally. Okay. So shear stress in the spring is coming tau equal to Kb 8 Fd by pi d. This is the formula. And what is the value of Kb? Kb equal to 4c plus 2 divided by 4c minus c. And what is the c? C equal to diameter, mean diameter of the whole spring divided by the diameter of the wire. Now, so this is the maximum shear stress. This is the correction factor. This is the value of C. Now we need to figure out one thing, that what is the deflection in the spring. It figured out by another formula. Let's see what we have in the slide. Okay. So we derive this formula for shear stress in the spring. This is the value of Kb. Now, to figure out the deformation that we apply force F, how much will be spring will deflect, say this much. So what is this value? If this value of y, this value we need to figure out. So this value is figured out by Castigliano methods to relate the force and deflection. That means we figure out by strain energy. In the when you take the free body, how many forces work there? There is a torque work there, and also the force work there. Okay. So by this formula, this is the main formula. We are not showing you that how this is coming. This little bit bigger. Okay. So from here, you got this formula, then you put the value of D. You put the pi dn, total length of the wire. Total length means this length from here to here. So you figure out the length of the single coil, 2 pi d to pi r, right? Then multiply the number of turns. You got L equal to pi dn. Then this is the area, this is the J, everything you put it over here. Then what is the deflection? Deflection y equal to del u by del f. You differentiate this one, then coming this one. Then after simplification, we got value of y. Y means deflection of the spring, coming this one. Y equal to 8f d cube n divided by d to the power 4g. What is the n over here? N is the number of turns in the spring. So that we did. We just put over here what is the deflection of the spring. So deflection of the spring delta equal to y 8m d cube n d4 g. Now, how you will figure out the spring constant? So feeding constant k equal to f by y or delta. That means amount of force needed for unit deformation. So from here you can figure out f by y value. That would be the k. And use as GRNs, you get this one. K equal to f by a, right over here. So for k, we are getting this one. d4 into g, 8d cube into m. So n is the number of turns in the spring, g is the shear modulus or modulus of rigidity, and k is the spring constant. Okay. So in this, there is a lot of things in the spring. Normally with the end condition, you see this portion little bit flat end condition, right? Then there might be not flat, that coming whole spring wire. Okay. Similarly, at bottom also have a little bit flat. Okay. So depending on end condition, there is some other correction factor used in the spring, helical spring. But that will teach you in the machine design class. We already know how you can figure out the stress in the helical spring. Okay. And the spring bearing, then all those things is called machine component, not the structural parts. Normally, if you know your applied force, how much deformation you want, what type of material you want, and if you have that data, then you can go to some company's website to make the spring, then you see which one matches with you. Say you need a spring with spring constant K equal to 1.115, say kilonewton per meter or per millimeter, centimeter, whatever. You need the spring. And obviously, you know what will be the mean diameter of the spring. Then with that data, you look to the website or handbook or catalog that which company make this kind of spring. Say your spring diameter is coming 26 centimeter. Now looking that which one is close match with this one. And after you looking the catalog, we found this one. K equal to, you're getting 2 kilonewton per millimeter, and diameter of the spring you are getting 25 millimeter. Other one you might find K equal to 1.8, same unit, and we get D equal to 24 millimeter. So you see it exactly we are not getting. Then as an engineer, you have to decide which one you take. Either you have to take this one or have to take this one. But if you work in a special program, like you work in a robotic program that is sent to the Mars or space mission, in that case, you're not getting exact matching, right? In that case, you can call to the company, hey guy, I need a spring. This will be the spring constant. This is the measured diameter. This will be the free length of the spring, L equal to this much. Could you make for me? I want this material. Then they will make it for you. Okay. Otherwise, you have to go through the company catalog, whichever product coming very close to your requirement. Because making a on spring is expensive. Okay, now solve problem. Same thing we described in the slide, whatever you see in the slide, all the formula. Okay, problem 1. It's a determine maximum shear stress. That means you need to know the tau. And elongation. Elongation means y or delta value. That you need to figure out y or delta. Tau equal to what? Y delta equal to what? In the bronze helical spring of 20 tons, that means N equal to 20. 1 inch diameter wire, that means small d equal to 1 inch. Then mean radius 4 inch, that means this big D equal to 4 inches. When spring supported a load 500 pounds, G is given over here. So F is given, 500 pounds. Value of Z is given. So one need to figure out maximum shear stress, how to be the tau and how to be the value of Y. So very simple. If you look to the formula, this is value of Y. 8F is given 500 pounds. Mean diameter of the spring is given. The number of turns is given. Diameter of the wire is given. And G is the modulus of rigidity of the material also given. So you put all the value right over here, you get the deflection of the spring. Now, how you get the shear stress? By this formula, KB 880 by dq. D is the diameter of the wire, 1 inch. And this big D, mean diameter of the spring, is also given. Mean diameter is 4 inch. Then N is given. Okay. And so 8F by dq. What is a KB? KB equal to C, 4C plus 2, 4C minus C. And C equal to big D by D. That means 4 by 1 equal to 1. So you put everything there, you will get the result, shear stress. If I like to know what is the spring constant, then use this formula. Or force already given. So you can easily figure out that spring constant K equal to applied force F divided by Y or delta Y. You already Y have this value and F already given 500 pounds. So very simple, you can use this formula. Now we'll solve problem 1. Any question? Anyone? Any question?
Sir, here
Yes.
we have determined shear stress at the outer surface of the spring. Now, if I want to determine what is the shear stress inside the spring material at a distance rho, then can I replace the D in the shear stress formula with rho?
Right over here.
Yes, sir.
This is the mean diameter
No, so small d with
of the spring.
Small d
And
with
this
rho.
small d is the, whatever you are saying, this is the wire, right? You bend the wire, and this is the radius. So how many forces are over here? So one is direct shear. My figure is not perfect. So right over here. So one is direct shear force working upward parallel to the surface. Other one, torque working anti-clockwise T, right? And F, you can easily figure out F by shear stress, F by A. And for the torque, you get shear stress tau, say this is tau. Tau equal to torque into radius divided by J. Now, when you design the shaft, a spring, then where you apply this R? You're thinking you like to figure out the stress at the center of the wire, then R will be 0, right? But if you particularly figure out right over here, then R will be certain value, not D by 2, right? So this is your cross section of the wire. So this is the maximum R. If diameter D, that R equal to small d divided by 2. So if you figure out the shear stress right over here, R0, no shear stress 0 due to the torque. But right over here will be maximum. Then you try to figure out this value will be less than outer, gradually moving to the center, the shear stress will decrease, and at the center, 0. Now, if you design a parts, we are thinking I take this radius instead the outer radius. Then what will happen? You get some value. Say your shear stress, you are getting 800 KSI, kilopascal per kilopound per square inch, right? So in that case, your result will not be accurate because maximum will be at the surface. So my question, why you take in the midpoint? If you like to say it, you can put it instead of, in that case, instead of R, you can choose whatever the distance from, say, your interested point is right over here. Then it choose distance. Okay. Your direct shear stress will be same, F by A. This is not depend on R. You have to take the whole area by d square. Plus this torsional shear stress, instead of R, you can suppose, say this is R1 from center to here, T into R1, you can take, divided by, you can take J. When you take the J, you have to take the whole cross section, okay? Then you multiply by correction factor, okay? It's possible to figure out, but when you like to design some parts, or you like to figure out what will be the maximum stress, then you need to choose the outer fiber. You got your answer.
Yes, sir. So J will remain as pi by 34 d to the power 4.
J will remain same. Why? Because J is the torsional resistance. If you increase the, okay, hold on 1 second, let me take your ID. Your ID?
So 018.
18, right?
Yes, sir.
Okay. And what I'm saying that you can take right over here. Over here will be maximum. It is possible to figure out the intermediate point, but you can, if you design by taking stress as intermediate point, your design will be wrong. Now you are saying what will be the value of the J? What is the J? J is pi by 32 divided into d to the power 4. What is J actually? We call it polar moment of inertia. What does it mean? That means if J value increase, shear stress will be low. When J value increase, you make the bigger. You make the smaller one, decreasing the value of D, then J will decrease. If J decrease, tau will increase. That means polar moment of inertia, it represents that if this value is high, then you need more torque, or it has more resistance against the torque. Because say I'm giving you a pen, small diameter, you can easily apply twisting, okay? But I'm giving a bigger diameter pen made of same material, then still you'll be able to rotate, apply torque, but you need to apply higher torque because bigger one has higher polar moment of inertia. So polar moment of inertia, you have to take the whole area because whole area will resist the twisting. Not only that you can think that intermediate diameter will resist the torque. No, the whole cross section will resist, will fight against the torque. Okay, clear?
Yes, sir.
Now we can solve the second problem. It's a compute the maximum shear stress developed in a phosphorus bronze spring say maximum shear stress. That means they like to know tau equal to what? They'd like to know this one. For the material, phosphorus bronze, having mean diameter of 200 millimeter. That means value of D is given. Consisting of 24 ton. 24 ton, that is the value of N. Of 20 millimeter diameter wire. So what is this 20? This data is given value of small d. So, yeah. So this 20 millimeter is the value of G. The wire, 20 millimeter diameter wire, then spring stress. Stress means we applied load to 100 millimeter. So that is given value of Y or delta. G value is given. So they say figure out the torsional shear stress. Not torsional shear stress in the spring. So what is shear stress formula? This equal to KB F D cube by, in the below there is some factor. Or this factor, if you look carefully, 8 into FD. So I make mistake, right? So there will be 8 divided by D cube. This is the formula to figure out the shear stress. Now you see, so again let me write down. We need to figure out the shear stress equal to KB into 8F into small d. I think into bigger D. 8 into FD. If you look over here, big D. Okay. So big D by D is the, so you see D value is given. Then number of N we don't need it, right? And this small d is given over here. So what is the missing over here? What is the KB? KB equal to 4C plus 2, I think, then 4C minus 3, something. And C equal to big D divided by small d. So you easily get the value of C. But you need to figure out the value of F. But you see, Y value is given. So from Y value is given, at first you figure out the spring constant. From the spring constant, you figure out the value of F. That F you put in this formula, you will get the tau. So let's see how we can solve it. Right over here. Diameter of the spring is given, big D, 200 millimeter or 0.2 meter. Number of turn in spring, you can put capital N, no problem, N equal to 24. Diameter of the wire, 20 millimeter, converting meter. Deflection in the spring, 100 millimeter, converting meter. G value, gigapascal, converting meter square. Okay. Now, tau equal to, you got this value, this formula. KB, you know this formula. And this is the value of delta. You see, F is not given. delta is given. If delta is given, then you can figure out the value of F from here. The value of F is you found. Also, you can figure out the spring constant. Spring constant equal to F by delta. So, deformation of the spring is this one. So, F by delta equal to how much? This. And F by delta is the spring constant. So, this equal to F by K equal to this. And right over all values given. Small d value we know, G value given, the mean diameter of the spring is given, n equal to 20 ton, right? No, 24 ton is given. So after put all this formula there, you will get value of K is 4.33 Newton per millimeter. That means if you like to make 1 millimeter deflection, you need to apply about 4.5 Newton force. Now, we can figure out the shear stress by using this formula. But how will get the value of F? We know spring constant. Delta value is given. Delta equal to, that means deformation in the spring 100 millimeter. Is deformation is 100 millimeter. How much force you need? For 1 millimeter, this mass is the force. So F equal to K into delta. So we got this mass Newton F. So now you put M value over here, you will get the value of the tau. And KB equal to this one, 4C plus 2, 4C minus C. C equal to big D by D. So this is the F value. F value, you put it on the formula, you get value of the tau. Then converting megapascal. So any questions regarding this spring problem? Any questions? No? Hello? No question? Okay, I am giving you 5-minute break. Then come back, we'll start the new chapter. Okay, that is called combined stress or mode circle. That is very interesting. Okay, so come back at 10:36. Okay, so I am putting you on break. So some book they mention as a chapter name as a mode circle, but I put it like combined stress. So by what combined, you might be realize little bit, right? That it is a combination of stress, combined stress. So what happened that for beam, how many stress in the beam? Rosdul Islam, roll 29. You are there? Rosdul Islam? You are not there. Niaz, roll 12.
Yes, sir.
Okay, tell me, how many stress in the beam?
Sir, can you repeat the question again?
How many stress in the beam?
Shear stress and bearing stress.
Not bearing. Shear stress and what is the other one?
Torsional stress, sir.
In the beam, I am talking about the beam. In this beam like this one, right? Say two support, on simple support, other one on pin support, we have a load over here. So how many stress will be in the beam?
Normal stress.
Normal stress.
And
Shear stress.
not normal stress, bending stress. Bending stress, sigma, and shear stress, tau. And is this beam is little bit thick, then it will bend like that, right?
Yes,
If
sir.
it is bent like that, what type of stress will be over here and over here? What type of stress will be here?
Sir, upper one is the bending stress and the lower one maybe shear stress.
That is shear stress.
So upper one is
Upper
compression, below one is tensor.
Okay, what's your ID?
So 18.
18. Good. Okay. That means two stress developed. Shear stress will try to break the beam in two parts. And bending stress, it will try to bend the beam coming from the bending moment. So is bending like that, that means this fiber will feel compressive stress, this surface, and outer surface will be tension. Similarly, if we apply load from the bottom, then it will bend like that. What does it mean? Right over here is a tension, and the bottom there will be compression. Okay. So this bending stress formula, sigma equal to MY, right? Or you can say MC, anything over I. Due to what happening over here actually. For example, if I apply, say, I apply bend, what will happen? How it will bend? Anyone? That means it will bend like that, right? So upper will be compression, bottom will be tension. This one you can explain in other way. How? Say this is my beam and depth of the beam, this height is h. So this m, right? This m, I like to replace with two force. How can we? Say one force working along this direction, other force working along this direction. How much will be moment between them? If distance is h, so moment will be f into h, right? So f into h will be equal to m. So what will be the f? F equal to m by h. So this m I can represent with two opposite force. One force working along this direction, other force working along this direction. This is whatever anti-clockwise. Still, this is anti-clockwise, right? Similarly, this m in the left side, I can replace by a compressive force and also by this force. Which direction is rotating? Clockwise. This is clockwise. Now, if you look carefully, that upper fiber, what happened? Compressive load or tension load? This fiber. If you here, you see upper portion is feeling compression, right? Right over here, this force working along this direction, this force this direction. That means this above neutral axis will feel compressive. And below neutral axis, that means the bottom fiber will feel tension. Right over here is tension, this is compression. So when it beam bend like that, that means one portion feeling compression, other portion tension. And this tension compression coming from the bending stress formula. That means sigma equal to MC over I. Okay. Now, what is the shear stress? Tau equal to VQ by IB. Where shear stress work? Shear stress work parallel to the cross section. Okay. So if I draw it again, that this is, let me draw the middle section right over here. So right over here, we figure out that there might be compression at the top due to bending, tension at the bottom. And also there was shear stress or shear force. So which direction shear force work? Parallel to the cross section. So everywhere shear force working downward or might be upward, but parallel to the cross section. So if I take a point in the beam, say right over here, in this point, how many force is working? One is compressive stress, right, due to the bending. Other one, downward shear force. But what will be the combined effect of these two? We didn't calculate when you learn the beam, okay? But this combined effect will be severe. What will happen? This portion try to squeeze, say this portion, this point, due to the bending moment, he will try to move toward left direction due to compressive. And the shear force try to pull him downward. So one force try to pull him downward, other force try to pull him along this direction. So the resultant direction will be along this direction. This will be resultant stress. That means resultant of shear force and the bending stress will be this stress. So what we got up here, we figure out the combined effect of shear stress and bending stress. You can call it normal stress too. Combined effect of shear stress and the normal stress. Okay. So similarly, say you have a bar, and the one end is fixed, attached to the wall or something, and you try to twist, and on up for your friend try to pull. So what you see over here, say pulling, applying F, and you apply torque T. So you see there is two forces on it. And you look in the stress, what will be the effect of the stress? Due to the torque, there will be torsional shear stress, tau. Tau will be TR divided by J. Right? We try to break this bar into 2 points. And this axial force is tension. So this creates axial tension stress. This equal to F divided by A. Now, if you consider as a point over here, what will happen? This point. This force try to pull him along this direction, right? And torsion try to break at this point. So he tried to make it crack. Right? It might be downward or upward. In this case, is torque is put clockwise, so I put the downward. So two resultant will be higher than both of them, right? Say this one 60, axial force 40. What will the resultant? Higher than 40 and 60, right? The root over this will be 1600 plus 3600, right? 5200 square. So if you are not considering the combined effect, then what will happen? your design will be wrong. It might be break down your parts. For example, my hand. Okay. So it's supported right over here, right? It at the knee. So some of our friend coming try to twist my hand, and other friend pulling the hand. So to force, effect will be severe, right? You will feel more pain. Say you are fighting with your friend. So one friend is coming, he's just pulling your hand. You'll get pain. You try to protect yourself, right? But this time, two friends coming and intentionally twisting your hand and other friend pulling your hand. So obviously you'll get more pain. Why? If you like to explain in terms of solid mechanics, how we can explain that why you get more pain? Because this time their combined effect will be severe than these two. Say, or your younger brother pulling your hand, you will not feel pain. Other younger sister twisting your hand, you will not feel that much pain. But if both together, pulling and twisting, then you might get pain. Because their combined effect make severe or make worse than individual force or stress. So this chapter talk about that if a structure has multiple load, then how we can solve, how we can figure out the stress in the body. Okay. Other thing is say a body is pulling along this direction and pulling along this direction. Cross-sectional area is A and amount of force is Z. So what type of stress will develop? Anyone?
Tensile.
Tensile stress. You represent by what? Sigma, right? What is your ID?
Sir, 18.
18. Okay, good. So how will you present? We figure out the formula. What will be your formula? You represent by tau or sigma? This is normal
Sigma.
sigma. So sigma will be F by A, right? Is there any other stress in the body, in that body developed? Yes or no? Ashkur Rahman, roll 36. You hear? Ashkur Rahman is not here. Okay. Let's see. Tasdeeq Chaudhary, roll 102. You are here? 102 is not here. 73, Mehdi Hassan, Ridoy. You are here in the front of computer, Mehdi, roll 73. Is not here. 91, Iftikharul Islam.
Yes, sir.
Okay. Tell me, we figure out that there will be stress, sigma. Is there any other stress in that body?
I don't think so, sir.
You don't think so? What is this one?
No.
Say, for example, you have ceiling in your room. You are sitting in a room, and from the rooftop, you have a rod, you hanging a fan, right? So fan has a weight. That weight working downward, right? And roof reaction will be upward. That means this rod will be under tension. That reaction will work upward and weight of the fan working downward. Similar example we put over here. So my question, we figure out that stress in the body is only sigma. Now my question, is there any other stress in that body? No one, right? We say no. But actually there are some stress work. Depend on how you look to the body. So we found sigma equal to F by A. We'll cut the body. Okay. If I cut the body, let me erase that one. And which way I'll cut? Let's see. I'm cutting this body in a certain angle. Say with this angle. This is stress body. So in the bottom, my force F is working, right? There. So I cut it in certain angle. Say this angle make me theta. So how much will be force over here? Obviously, upward direction, same force, because this tension force, right? Now, this force is working upward, but I can split this force into components. How? If I make the triangle outside, second, let me take the straight line. Say this is my straight line. This is the angle, right? This angle theta. Theta, and outward direction F force or, and this force is F. Now I like to split this force into components. How can do it? If I make a straight line, let me pick up other color through this point. Okay. Now, what will be this angle? This angle will be theta, right? Theta. How much will be this angle? 90 minus theta. Or if I can make one more line over here perpendicular to this surface, then this angle will be theta. Okay. So right here, this F I can make in two components. Along this direction, I can say this component will be F cos theta. And along this direction, or perpendicular of this direction, is F sine theta. I can write down, right? So along this direction, force working F sine theta. And along this direction, force working F cos theta. So what do you see now? You see this F sine theta is working parallel to this surface where I cut it with certain angle, not this one. Cut it certain angle. And F cos theta is working perpendicular this surface. Okay. If I like to make a 3D, then it will like that, right? So this F sine theta working this surface along this direction. So this is shear force. And F cos theta working from normal to this surface outward, the F sine theta. So even right over here, you see only normal force is working, no shear force. But if you cut the body in a certain angle, then you see there is one shear force and one normal force is working. That's why what will be happen if you say you have a bar and if you apply higher load along this direction under tension, what will happen finally? You gradually increase the load. What will happen? Anyone? Your stress will be developed F by A, and gradually you increase the area. Then finally, what will happen?
It
Anyone?
will fail.
It will fail. How it will fail?
If it's ductile, then it will fail in straight line.
Straight line. Rashid, roll 90. You are here? Rashid, roll 90. Okay. It will fail. That means it will become two part. Finally, right? How? Yeah, you might do it test and solve. Gradually, there will be, it will go bigger, the length will increase, this portion will shrink, and at the final, there will break down over here, become two part. So, what is our theory? If something break down in two part, shear force is working. So, you see right over here, we don't apply any force, shear force or normal force, but inside the material, shear force is working. So it depends on which way you are cutting. Say you are cutting in 0-degree angle, then there in that plane there will be only the normal force. But if you are cutting at a certain angle, in this angle, cut this angle, any angle you can cut. And we found that if you cut it at 45-degree angle, that at that point shear stress will be maximum. Okay. And so remember that thing. Okay. So what happened? We need to know that if you use a ductile material, is very brittle. It cannot take tensile load. It automatically fails. So if you use a ductile material, then it will take the tensile load, but it might fail due to the shear, depending on what type of material. So to figure out the combined stress in a structure, we need to know some definitions. For example, you like to buy a computer, you need to know what is the RAM, what is the CPU, what is the hard drive, what is the gigahertz, megahertz, right? So let's see, go through the slide. So we need to know two things, two definitions. At first, it is called number one, plane stress, other one is called plane strain. And you need to remember that from this chapter, there will be one full question. Okay. So plane stress. Plane stress is defined to be a state of stress at which normal and shear stress are zero in the direction perpendicular to a plane. For example, this is a notebook, right? You think this is a metal plate. So if I pull along this, I can pull along this direction, or I can pull along this direction, right? So if you think this is a x-axis, this is y-axis, vertically z-axis. That means I am not applying any force along z-axis. All the force working along only xy plane. This type of situation, we call it a plane stress, because all the force is working in one plane, and perpendicular this plane, that in z-axis, there is no stress. So it's saying stress in z direction will be zero for xy plane, but strain in z direction is not zero. So what happens? Say if I pull along x-axis, length will increase. What will be the stress? the force divided by this area. That would be the stress along x-axis. If I pull along this direction, if this is the area divided by Fy, force along f direction, you will get the stress along y direction, right? If you pull along this direction, what will happen? Length also increase. That means you will have the strain. What is the strain? Original deformation divided by original length. Similarly, if you pull along this direction, stress will be there will be stress and also strain. But what will be the along z direction? There will be stress 0 because there is no force. But what about the strain in z direction? There will be strain because you gradually pulling this paper or plate, the thickness gradually decrease. If you compress, thickness gradually increase. So this type of phenomenon or state of stress is called plane stress. Other thing you need to know, the plane strain. What is the plane strain? It is defined to be a state of strain in which strain in the direction normal to a plane is assumed to be 0. What happened? Say, my phone. You think this is a metal plate. So if I pull it on the both xy plane, then what will happen? The thickness will gradually reduce. And ultimately, if you increase the force, it will break down, right? But you think that initially, this plate thickness is 4 feet. 4 feet thickness, you are pulling along this direction. You are pulling along this direction. In that case, theoretically, you will see the thickness will gradually decrease. But with respect to the length is 4 feet thickness, you might have decreased the thickness 0.001 inch divided by 4 feet means 48. That value will be very low value, right? So in that case, we can say that strain in the z direction is 0. So you have all the force in xy plane, but thickness is very high. Perpendicular direction, thickness is high. So if we apply the load in xy plane, theoretically thickness will be decreased, extremely very low value, but we can ignore that. So this type of situation is called plane stress. I'm sorry, plane strain. Okay. So it's saying it is defined to be state of strain in which strain in the direction normal to the plane is assumed to be 0. It is normally happen if dimension of the structure in one direction, say z direction, is large in comparison with dimension in other two direction or xy direction. Strain in z direction will be 0 for a xy plane load. For example, say you have a pipeline from Dhaka to Kumilla. You know, we study pressure vessel, right? In the pressure vessel, what type of stress is working? Longitudinal stress, sigma L, right? One is sigma L, other one tangential stress. What is the sigma L? Sigma L try to split the pipe into 2 parts. That means they try to pull him like that. So in that case, what would be the increase of length of the pipe? Somebody pulling in both directions, right? Due to the pressurize. In that case, compared to length, the strain means change of length divided by original length. So this change of length will be extremely low. Then you divide it by a long number. So this value will be close to 0. So for simplification, sometimes we assume that the thickness of the parts become extremely higher than the other two directions, that in the high direction, there is no strain. Okay, so it's saying it is defined to be a state of strain in which the strain in the direction normal to a plane is assumed to be 0. It is normally happen if dimension of the structure in one direction, say Z direction, is large in comparison with dimension in other two directions. So strain in Z direction will be 0 or if load in the XY plane. Sometimes this definition come in the exam. They define what do you mean by plane stress and plane strain. Now, stress in a body. You see right over here. Right over here, you see a arbitrary shaped structure. For example, you went to select and top of a hill, you see there is a stone, right? And you sitting over here, somebody pulling along the direction, some of the square is kicking too. This is the reaction, and somebody sitting over here. But this stone is not moving. What is the reason? Is not moving. Anyone? Anyone? Rashid Hassan Hussein, roll 90. You are here? Rashid? Roll 90. Rashid? You're not here. Bishal, load 23. You here?
Yes, sir.
You here? Bishal? Hello?
Yes, sir. Yes, sir.
Okay. Bishal, you are here, but I see your mic is unmute. Then how come? Who is talking? Is it Bishal?
Yes, sir. I'm Bishal, sir.
Okay. Roll 23.
Ji, sir.
Okay, got it. Tell me, you went to select with your 10 friend, and you got up the hill and sitting in the stone. Somebody sitting, somebody kicking, but stone is not moving. What is the reason? We are applying the force. What is the reason? You can tell me?
Sir, because some net issue, I can't hear it clearly, sir.
You cannot hear clearly. Okay.
Hello?
You are sitting or you are standing in the room?
Sir, I'm sitting in my room.
Sitting in your room. Okay. Say you have 3 younger brothers. You're sitting in a chair and 3 brothers try to, somebody kicking you, somebody try to pull, but still you are sitting in the chair. How? You can explain in terms of solid mechanics and incident mechanics.
Sir, I can't.
You can? No, you have to. Okay. That means summation of all force and reaction is equal to 0. You are sitting on the chair, your younger brother tried to pull it, but he resisted. That is your reaction. So when your reaction and applied load become equal and opposite, then it will not move. Okay?
Sir, isn't it because of center of gravity is not changing?
No, center of gravity, why is not changing? Center of gravity is changed, then it will move. Why is not changing? Because say right over here,
force and
weight
applied
working
force are 0, sir.
downward, right? So how many the force? External force plus weight plus reaction at the ground. All summation of the all force that you learn, summation of Fx is become 0. Summation of force,
Fy equals 0, sir.
yeah, y 0, z 0.
And also the moment is 0, sir.
Yeah, moment is 0. That's why it is not rolling. Okay, sometimes say it is not moving, but it might be rolled a little bit.
Slight and
Okay, but it is not rolling, that not tilting. That means summation of mx equal to 0, my
But,
equal to 0.
But sir, if it falls, then it has to be rolled. Otherwise, how can it fall?
What you say?
It can
No,
fall.
it's not falling. I'm saying it is not falling down, it is not breaking. It remains the same. But your 1520 fan is getting on that stone and they are kicking, somebody sitting, but it is not moving. What does it mean? That means somebody sitting. What is the force? His body weight working on the stone that I show you with a say arrow right over here. But still it is not moving because summation of all force and the reaction force, algebraic summation, is become 0. That's why it is not moving.
Sir, also
Then-
the gravitational force is working. So the summation of the body weight and the gravitational
Yeah,
force.
all force. All force mean summation, also summation of weight. So this is in the, say, this is the heel, right? So
Yes, sir.
they are also working reaction force at the working upward. So this all the force, reaction force, then this weight, then somebody sitting over here, heat weight is working downward, somebody pulling, somebody kicking. So all summation of the all force equal to 0. That's why it is not moving. Now, tell me, why it is not breaking? It is not moving, but if it is a very brittle material, you sit down to fan, it might break right over here.
Blink means sir, break, sir.
What do you say?
Your question, sir. You are asking.
Yeah, my question, why it is not become two part?
Because the forces are not enough to break it.
To break, good. That means it has internal resistance, right?
Yes.
So
Yes,
that resistance is higher than the applied load. Okay. So what's your ID?
Sir, 12.
Well, okay. 1 second. So you see, it is not breaking, it is not rolling. Now, if I like to take a section, it's a dotted line, I like to cut with the knife, and I like to say the how many forces are in there. So you see, so if I cut it, our time is over. We finish up this slide. We'll get this cross section. So in that cross section, you will see only there is two force work. One is normal force, other one is shear force. That I already show you with a by splitting a like this kind of body with certain angle theta, right? If you cut like that, there will be a shear force working along this direction and normal force working perpendicular to the surface. So if I cut it right over here, then there will one normal force will work perpendicular to my screen, and shear force will work along this direction. So that is showing over here. That means along x direction, there will be a normal force, sigma. And there might be any direction, there will be one tau. There will be a tau. The combined effect of this sigma and tau, if it is higher than the applied load, then it will not break. But if tau and sigma is lower than the applied load, then the stone will be breaking to two parts. So this tau, say working along, if I see this is x-axis, that means going to the screen, and this is y-axis, this is z-axis, then this tau I can break into two components. One component will work along this direction, other component will work along this direction. That means at a single point, there is one normal stress or perpendicular to the surface and two shear stress work along two axes. So that one they explain it a little bit over here. So this direction is working tau. They mentioned over here. Along this direction working sigma. And this sigma, this is the z axis, and this is the y axis. So this is sig x. So we have sigma x because we cut perpendicular to the x axis. Now this tau we can divide into component. One component working along this direction, vertical direction, and other component I can say work along this direction. So this is the two tau right over here. One is tau xz, other one is tau xy. Okay, that means if you cut a body, then at that point there is three stress work: one normal stress and two shear stress. Okay, so you just remember that thing for the next class. Okay, any questions so far? Any questions? Anyone? Any questions? No? Okay.